Welcome to Methods in Biostatistics. Today, we are diving into two of the most fundamental concepts in all of science: central tendency and dispersion. Imagine you are a wildlife biologist measuring the weights of hundreds of sea turtles. You cannot just hand someone a notebook full of numbers. You need a way to summarize that data, to find the typical value, and to understand how much those weights vary from one turtle to the next. By the end of this video, you will understand exactly how to transform raw, chaotic biological data into clear, meaningful scientific insights. Let us start by understanding why we need measures of central tendency. In the biological sciences, you will often collect massive amounts of data. If you want to know the typical weight of a sea turtle, or compare the blood pressure of patients on a new drug versus a placebo, you cannot look at every single data point at once. You need a single representative number that captures the center, or the typical value, of your entire group. This middle ground acts as a reliable anchor point. Without it, comparing different biological groups would be practically impossible. Choosing the right measure ensures our scientific conclusions are valid. Now that we know why we need a central value, let us look at the three most common ways to find it. The first is the mean, which is simply the arithmetic average of all your data points. The second is the median. If you line up all your data from smallest to largest, the median is the exact physical center. It is incredibly useful because it is resistant to extreme outliers. Finally, we have the mode, which is just the most frequently occurring value you observe. In biostatistics, we often look at all three because relying on just one can sometimes give a skewed picture of our typical patient or organism. Let us translate the concept of the mean into its mathematical formula. The formula for the sample mean is x bar equals the sum of xi divided by n. Here, the symbol x bar represents the sample mean we are trying to find. The Greek letter sigma is a command that tells us to add up all the following values. The term xi represents each individual data point in our sample. Finally, the denominator n represents the total number of observations. Conceptually, if the total number of observations n increases while the sum remains stable, the mean will decrease. This shows exactly how sample size impacts our central value. Before we move on, let us see this with a concrete example. A nurse measures the resting heart rates of 5 patients, recording 72, 76, 72, 80, and 70 beats per minute. We want to find the typical heart rate. First, we calculate the mean by adding all 5 values to get 370 and dividing by 5, giving us 74. Next, to find the median, we must sort the data from lowest to highest. Since we have 5 patients, the third value is our exact middle, which is 72. The mode is also 72, as it appears twice. Physically, this tells us that while the average is pulled up slightly by the patient with an 80 heart rate, the most typical, centrally located heart rate is 72. So we have successfully found the middle of our data. This brings us to an important realization. Central tendency alone is not enough. Imagine 2 hospitals. In Hospital A, 3 patients stay for 5, 5, and 5 days. In Hospital B, 3 patients stay for 1, 5, and 9 days. Both hospitals have an exact mean of 5 days. But the situations are completely different. Hospital B has much more unpredictability. This is why we need measures of dispersion. Dispersion quantifies the spread or scatter in a data set. In biology, natural variation is expected. Measuring this spread tells us how reliable our mean is and whether our data points are tightly clustered or highly variable. To quantify this spread, we use a metric called variance. The formula is S squared equals the sum of xi minus x bar squared, all divided by n minus 1. Here, S squared represents the sample variance. Inside the parentheses, we calculate how far each individual data point deviates from the mean. We square this difference so that positive and negative deviations do not just cancel each other out to 0. The denominator, n minus 1, is called the degrees of freedom. We subtract 1 to correct for the fact that a sample usually underestimates the true variation of a full population. If data points move further from the mean, the variance grows larger. This formula we just saw leads us to an important question. How do we interpret variance if it is in squared units? The answer is the standard deviation. The formula is simply S equals the square root of S squared. By taking the square root of the variance, we reverse the squaring process we did earlier. This is absolutely crucial because it converts our measure of spread back into the original units of our data. Having the spread in the exact same units as the mean makes it physically meaningful and incredibly easy to interpret in the real world. If the standard deviation is small, the data is tightly clustered around the mean. Now that we have our formulas, let us calculate the spread for Hospital B, where recovery times were 1, 5, and 9 days. We know the mean is 5. First, we find how far each patient deviates from the mean, giving us -4, 0, and +4 days. Next, we square these deviations to make them positive, resulting in 16, 0, and 16. We sum these to get 32. Since we have 3 patients, our degrees of freedom is 3 minus 1, which is 2. Dividing 32 by 2 gives a variance of 16 days squared. Finally, we take the square root of 16 to find our standard deviation. The final answer is 4 days. Physically, this means a patient's recovery time deviates from the 5-day average by about 4 days. Let us look at what this dispersion actually looks like visually. On this graph, the horizontal axis represents the value of our data, and the vertical axis represents how frequently those values occur. Notice the dashed line in the center. Both curves share the exact same mean. However, the tall, narrow blue curve represents data with a low standard deviation. The data points are tightly packed around the center. In contrast, the short, wide red curve represents data with a high standard deviation. Just like our Hospital B example, the data is highly spread out. This diagram beautifully illustrates why knowing the mean alone is never enough to understand the true shape of your biological data. Now that we understand standard deviation, we face a new challenge. Suppose you are studying elephants and mice. An elephant's weight might have a standard deviation of 500 kilograms, while a mouse's weight varies by just 10 grams. If you only look at those absolute numbers, you would think elephants have vastly more natural variation. But this is an unfair comparison, because an elephant is massively larger to begin with. Comparing kilograms to grams is literally comparing apples to oranges. To solve this, biologists need a way to measure relative spread, a metric that is completely independent of the units or the overall size of the subjects. This need for a relative comparison brings us to the coefficient of variation, or CV. The formula is CV equals S divided by X bar, multiplied by 100%. Here, S is the standard deviation, and X bar is the mean. By dividing the spread by the average, we are calculating what fraction of the mean the standard deviation represents. Because we divide a weight by a weight, or a length by a length, the units completely cancel out. Multiplying by 100 simply converts this decimal into a readable percentage. If the standard deviation increases while the mean stays the same, the CV increases, indicating a higher relative variability in your population. Let us apply this formula to our elephants and mice to see which animal is truly more variable. For the elephants, we are given a mean weight of 5,000 kilograms and a standard deviation of 500 kilograms. Dividing 500 by 5,000 gives 0.10, which is a CV of 10%. For the laboratory mice, the mean is 50 grams, with a standard deviation of 10 grams. Dividing 10 by 50 gives 0.20, which is a CV of 20%. Physically, this is a profound result. Even though the elephant's absolute variation of 500 kilograms is numerically huge, the mouse population actually exhibits twice as much relative variability compared to its tiny size. The CV uncovered a biological truth we would have otherwise missed. We have covered a lot of ground today, so let us summarize the key takeaways. First, measures of central tendency, like the mean, median, and mode, help us find the middle ground, giving us a typical value for our biological data. Second, we learned that the center is not enough. We must measure dispersion using variance and standard deviation to understand how spread out our data truly is. Finally, when we need to compare completely different data sets, the coefficient of variation levels the playing field by providing a unitless percentage. Together, these tools allow you to transform raw, chaotic data into rigorous scientific insights. You are now ready to analyze biological diversity with confidence.